Your lecturer is James W. Gregory. Dr. Gregory is a professor of mechanical and aerospace engineering at The Ohio State University. He received both his MS and PhD in aeronautics and astronautics from Purdue University. Dr. Gregory is an instrument-rated private pilot with more than 200 hours of flight time in gliders, single-engine aircraft, and multi-engine aircraft. His work experience includes stints at the Air Force Research Laboratory Air Vehicles Directorate, Delta Airlines, NASA's Glenn Research Center, and Tohoku University in Japan.
For millennia, humanity has wanted to reach into the heavens, to fly above the planet. We have seen this in numerous instances throughout our history. In Greek mythology, Daedalus and Icarus fashioned wings of feathers and wax to try to fly. Leonardo da Vinci sketched flying machines and helicopters in his notebooks. In 1783, the Montgolfier brothers were the first to build a hot air balloon that successfully flew. In the 1890s, Otto Lilienthal built gliders, and in 1903, the Wright brothers built the first powered aircraft that was practical. It has been this constant of trying to break the bonds of Earth that has fueled our efforts to engage in flight. From all of those early efforts and all of those early desires, to where we are today, being able to fly around the globe in less than a day, and being able to fly into space to explore the bodies of the solar system. It's a remarkable experience when you think about it, how humanity has moved from where it was to where it is.
On August 29, 2006, in the Patagonia region of Argentina, the adventurer Steve Fawcett set out to break yet another world record in aviation, pushing the very boundary of what is possible. His goal? To break the absolute altitude record for an unpowered glider. Now, Fawcett had already had a trophy case full of aviation records, accomplishments, and accolades. Most notably, he was the first person to ever circumnavigate the globe, flying solo, uninterrupted, and without refueling. He actually did this in a balloon between June 19th and July 3rd, 2002, flying in an easterly direction, starting and ending in Australia. And that wouldn't be his last time around the globe either. Fawcett went on to make a total of 5 non-stop circumnavigations of the globe in craft as varied as a sailboat, balloon, and airplane. So clearly, Fawcett was an aviation adventurer of the highest order. Now, this wasn't Fawcett's first attempt at the glider altitude record either. Over a period of 4 years, he had made 27 attempts at the record, all without success. The challenge with a glider is that there is no energy source on board to propel the aircraft higher. So Fawcett and his co-pilot, Einar Enevoldsen, had to use standing mountain waves to push their glider to increasing heights in an effort to break the altitude record of 49,009 feet set by Robert Harris in 1986. Standing mountain waves, or lee waves as they are called, occur when the wind flows over the top of a mountain ridge at a direction close to perpendicular to the ridgeline. Strong periodic regions of updrafts and downdrafts are formed, and the air can sometimes be highly turbulent, called clear air turbulence. In fact, these mountain waves are so strong that they have been known to cause commercial airliners to disintegrate in flight. It was into this kind of high-energy mountain wave in the Andes that Fawcett and Enevoldsen ventured in order to extract enough energy from the winds to take them up to new heights. And they did it. Their glider climbed to an altitude of 50,722 feet, a new world record for altitude in a glider. This is ultimately a demonstration of humans and nature in a dynamic relationship. The human effort to overcome the limitations of gravity, but also working with nature to extract energy from the winds to stay aloft. And that dynamic really is the science of flight in action. Flight is what captivates our imagination. Our pursuit of flight is propelled by longings for adventure, freedom, the spirit of discovery, and exploration of the unknown. From the sky, we can see where water has flowed and fascinating geometrical patterns left by human development. Other aspects of life are placed in a larger perspective from the air, where we can transcend national boundaries with ease. Perhaps no image has so transformed our understanding as much as the first photographs taken of the entire Earth as viewed from space. We have unparalleled access to areas of the world that we would never be able to reach, like dropping in on an inviting but remote riverbed in the Alaskan bush, or flying into the high-altitude confines of Pero-Baton and its Deep Valley Airport. And then there are our technological marvels, from the Wright Flyer to the Beech Starship, Spaceship One, or the Northrop Grumman B-2 Flying Wing. We're invited into a deeper exploration of how these flying machines work. Even though I have been working as a scientist and engineer on aircraft for my entire life, I still stand amazed at the marvelous achievement of flight. Watching a large 747 gracefully make a final approach to landing is a beautiful and awe-inspiring moment. And an air show with high-performance fighter aircraft in precise and coordinated flight is breathtaking. But perhaps the best way to begin our foray into the science of flight is by looking at gliders. The act of gliding is flight in its purest and most basic form. Just a pilot and wings, working in an attempt to tame the wind and soar like birds. Gliding is also where the earliest pilots and designers started their efforts towards airplane flight. Otto Lilienthal built famous gliders near the end of the 19th century, but died in a crash before he could do more. The Wright brothers initially learned many of the nuances of flight by first taking to the air in gliders. And gliding flight isn't some quaint corner of aviation. It affects what happens to any aircraft whose engine fails, which does happen occasionally. A pilot who has lost all thrust cares immensely about the glide performance of the aircraft. And there are intrepid adventurers, such as Fawcett and Enevoldsen, who pursue glider flights to push the boundaries of what is possible and study the atmospheric science of the stratosphere, which may even have lessons for how to fly in the thin atmosphere of Mars. Now, when a glider climbs in altitude, what it's doing is increasing its potential energy. But since there's no engine on board to increase the glider's energy, the glider must tap some kind of external energy source. From ground level, this increase in energy might be provided by a tow plane or a ground-based winch, either of which can boost the speed and height of the glider. For a glider already in high-speed flight, a pilot can trade off some of the aircraft's kinetic energy for potential energy by pulling up into a climb. The altitude is higher while the airspeed decreases. But most commonly, a glider pilot will look for external sources of energy within the atmosphere. Most often, these sources include thermals, which are rising masses of heated air. But at the highest altitudes, glider pilots need to rely on mountain waves, which are very strong periodic updrafts and downdrafts created by wind flowing over the top of a mountain ridgeline. Fawcett and Enevoldsen basically surfed on these mountain waves, soaring all the way up to their new record altitude of 50,722 feet. Sadly, it was the same kind of atmospheric phenomenon, a downdraft this time, that took Steve Fawcett's life in a powered aircraft on September 3, 2007, just about a year after he set his glider altitude record. He was flying in a mountainous region of Nevada in a super decathlon, and the crash investigation report from the National Transportation Safety Board, or NTSB, suggests that his aircraft simply couldn't outclimb a downdraft on that hot day and at those high altitudes, where the air is so thin. So the power of the winds that took him soaring to new record heights in a glider are the same winds that led to Fawcett's untimely death in a powered aircraft. It's a stark reminder that we can sometimes harness the wind, but we cannot always master it. There will always be an element of risk and danger, whether in a glider or in a powered aircraft. Pilots are always subject to the constraints and forces of the natural world. Glider flights at even higher altitudes pose some significant technical challenges. Let's take a look at some challenges of high altitude. The air in the atmosphere above 20 or 30,000 feet is thin. So thin that a pilot or passengers would not survive without some external life support. Glider pilots venturing up to these remote regions of the atmosphere must wear pressure suits, not unlike an astronaut's spacesuit, or fly in a special glider with a pressurized cabin. The thin air at altitude is why commercial airliners have pressurized cabins, which take compressed air from the jet engines and pump up the pressure in the cabin. But when the cabin pressure is raised to keep you breathing, there is exceptional force placed on the cabin walls due to the pressure difference between the inside and outside of the cabin. So the structure of the aircraft fuselage, or the main body, has to be built to contain over 1,000 pounds of force acting on every square foot of the cabin wall. If this structure isn't strong enough, the fuselage will pop like a balloon with an explosive depressurization. Also, the aircraft wing has to somehow provide enough lift to keep the aircraft flying. In the stratosphere, the rarefied regions of the atmosphere where commercial airliners fly, there's only about 1/3 of the air that we have near the Earth's surface. Since lift generation depends on having a sufficient amount of air to work with, the process of generating lift is so much more difficult at altitude, and it becomes a driver for the size of the wing. And the speed of the aircraft must come into play as well. The faster the aircraft moves, the more air molecules there will be that rush over the wing's surface, and the higher the momentum of that air will be. And finally, the angle of the wing with respect to the oncoming flow has a significant impact on the lift. This angle, called the angle of attack, dictates how much wing area is presented to the flow, affecting how much the airflow is disturbed by the wing's presence. Pulling these factors together, we see that the lifting force of an aircraft depends on how many air molecules are present, which is the density of air, the size of the wing, the angle of attack, and the square of the airspeed. There's a straightforward equation to express this fact. The lift must be equal to the product of 1/2 times density times the square of airspeed times wing area times something we call a lift coefficient. The lift coefficient goes up with angle of attack and is a measure of how hard the wing is working to produce lift. And here's a critical point. Any aircraft or bird in level flight must have its lift exactly equal to its weight for equilibrium to be maintained. So we can look at a 5-pound bird in flight and immediately recognize that it is producing exactly 5 pounds of lift. But if the bird wants to climb to a higher altitude, it must increase its lift for a short time to pull it up to that higher height. And if it wishes to descend, it must allow its lift to drop below the value of its weight. The other key aerodynamic force that glider pilots and designers worry about is drag, which acts on the glider against the direction of flight. If it weren't for drag, a glider could soar indefinitely. Drag follows the same trends as lift, since they are both aerodynamic forces. Drag also scales with air density, the square of the airspeed, the wing area, and a drag coefficient. The drag coefficient is a measure of how aerodynamically clean the glider is. The more streamlined and efficient the glider is, the lower its drag coefficient will be. Now, for gliders, in fact all aircraft, the key metric that defines the efficiency of flight is the ratio of lift to drag. Lift divided by drag. Since lift is desirable, but drag works against us, we can think of L over D as an efficiency metric. We want it to be as high as possible. For a glider, the distance that it can fly, if no further beneficial winds are encountered, is related to this lift-to-drag ratio. Let's see how that works. First, we'll define a glide path angle, which is the angle of the flight path referenced to a horizontal plane. Glide path angle uses measurements of the altitude and horizontal distance to determine where an airplane is expected to touch down based on its current trajectory. In other words, the glide path angle helps predict the spot where the airplane will land. Now there is a very important relationship between the lift-to-drag ratio and the glide path angle. This relationship is given by a simple but profound equation where lift-to-drag ratio is equal to the inverse of the tangent of the glide path angle. This is a compelling relationship that describes the glide performance of an aircraft. First, we have to take a look at the tangent of the glide path angle, gamma. Now, from trigonometry, the tangent function may be familiar as the ratio of the length of the side opposite of the angle to the length of the side adjacent to the angle. But the key thing to recognize here is that if the angle gamma is large, then the tangent of gamma is also large. The glide path angle is important because it directly dictates how far we can glide. We can easily see that by looking at a triangle representing the glide path. The hypotenuse is the direct distance that the aircraft travels through the air. The horizontal leg of the triangle is the distance covered over the ground, and the vertical leg of the triangle is the aircraft's height above the ground at the start of the glide. The glide path angle dictates the magnitude of our aircraft's horizontal glide distance relative to our height above the ground. The smaller the glide angle is, the longer our glide range becomes. So in order to get the best glide performance, we want to minimize the glide path angle. And to do this, we need to maximize the lift-to-drag ratio. In other words, we want more lift and less drag. Glider pilots such as Steve Fawcett know that they have to minimize their glide path angle to glide as far as possible, and that can only be done by flying the aircraft at its most efficient operating condition, where maximum lift-to-drag ratio is achieved. But how did he do this? Well, it turns out that the lift-to-drag ratio varies with airspeed, and a pilot can actually control airspeed during a glide. Now, it may be surprising for you to learn that the speed of an aircraft can be controlled even when there is no power available. Most of us are used to driving our cars, where if the engine quits, we coast to a stop, and we have no control over our speed. And it may seem like if the engines quit on an airplane, it might just drop out of the sky like a rock. Luckily, that's not the case. The pilot can control the airspeed in a glide by varying the angle of attack. The angle of attack is defined as the angle between the flow direction and the aircraft's wing. This is not the same as the glide path angle, which is between the flight path and the ground. Since lift is roughly constant throughout a flight and equal to the weight, we see from the lift equation that the angle of attack and velocity both come into play. So a pilot can slow an aircraft down by increasing the angle of attack. Or to accelerate, the angle of attack must be decreased. Now, even though lift is roughly constant across a range of steady flight speeds, the aerodynamic drag is not constant. For every airplane, there is actually a speed at which the drag will be minimized. At both lower and higher airspeeds, the drag will go up. So there's an airspeed for minimum drag. With constant lift, this then means that the airspeed for minimum drag is the same as the airspeed for maximum lift-to-drag ratio. And the condition for L over D max also minimizes the glide path angle, which will extend a glide as far as possible. So a pilot in a glide should fly at the airspeed for L over D max by controlling the aircraft's angle of attack. This is exactly what Captain Chesley Sullenberger did on his ill-fated Airbus A320 that he had to bring to an emergency landing on the Hudson River. On a cold January morning in 2009, U.S. Airways Flight 1549 took off from New York's LaGuardia Airport. As the flight gained altitude over the city, disaster struck. A flock of Canadian geese flew directly into the path of the plane's engines, and suddenly the aircraft was without power. This event turned the sleek, powerful A320 into nothing more than a glider. From a peak altitude of only 3,100 feet, Sullenberger's options for a safe landing were few. Thankfully, Captain Sullenberger was a highly experienced pilot with a lot of glider piloting experience as well. As he was looking for a suitable place to land, he perfectly flew the A320's best glide speed of just under 200 knots, or 230 miles per hour, by pitching the aircraft to the right angle of attack to get that speed. He could have tried returning to LaGuardia, and he considered diverting to nearby Teterboro, New Jersey. But neither option was a good one, since the glide distance of the A320 was only marginally sufficient to get him safely to either runway, and there was the dense New York metropolitan environment in between. So Sullenberger held the speed for best glide and lined up with the Hudson River. Piloting the crippled A320 just like a glider, he avoided all the infrastructure and densely populated areas of New York City and then brought the plane in for a water landing. All of the 155 people on board survived in what has widely become known as the Miracle on the Hudson. Now, how exactly can a pilot control the angle of attack on an airplane? Let's take a few moments to consider what control inputs the pilot has and how they are used to control the aircraft. At the most basic level, the aircraft has some form of control input that allows the pilot to control the aircraft's pitch, roll, and yaw. Yaw is the left-right dimension most familiar to car drivers. This points the nose to the left or right, and it's called a rotation about the vertical axis. Roll is a more extreme version of the tipping side to side that is familiar to a bicycle and motorcycle rider. On aircraft, roll is a rotation about the longitudinal axis, passing down the length of the fuselage, which banks the wings upward or downward to the left or right. And pitch is the dimension unique to aircraft, which is rotation about an axis passing through the wings, which points the nose up or down. Surprisingly, the method of control input hasn't changed very much over the past century of flight. The Wright Flyer had a control harness and a series of cables to translate the motion of the pilot's shifting body into a patented warping or twisting of the entire wing, which would roll the aircraft to the left or the right. But this technique was cumbersome and not very comfortable. We're at the Aviation Institute of Maintenance in Manassas, Virginia. I'm sitting in a Beech Queen Air, and we're going to take a look at the flight instruments and how they're put together. These are the six-pack of instruments here. We've got the airspeed indicator, attitude indicator, altimeter, vertical speed, the heading indicator, and the yaw bank coordinator. For the controls, I've got the control stick here for the roll control, pitching down and up. And I've got the rudder pedals here to yaw the aircraft left or right. If I'm coming in for a landing, I've got my flap switch here, which I can deflect to deploy the flaps. And I've got a landing gear switch here to put the gear down. And here's the gear indication lights for gear down or gear up, for a light for all three. Here's the throttle quadrant, where I've got the engine RPM, the pitch of the propeller, and the mixture. And then below that, I've got the trim controls, one for each axis of the aircraft: pitch, roll, and yaw. These are the main controls that the pilot will manipulate to keep the aircraft flying. Nearly every modern aircraft will have a control stick or control yoke and rudder pedals. The control stick can be a side stick, such as on Airbus or Cirrus aircraft, or between the legs, such as on many fighter aircraft. Most common on general aviation aircraft and Boeing's commercial airliners is the control yoke, which is mounted on a column like a steering wheel that can be pushed forward and back, as well as turned left or right. And these controls are always connected to three kinds of control surfaces: ailerons on the wingtips for roll, the elevator on the horizontal tail for pitch up and down, and the rudder on the vertical tail for left-right yaw. Each of these control surfaces is like a flap that changes the shape of the wing or tail to produce more or less aerodynamic force in a desired direction. The tail of the aircraft is also there to keep the aircraft flying straight in stable flight, where the aircraft must return to an equilibrium condition after it's been perturbed by a wind gust, for example. The horizontal and vertical tails on an airplane come from the same idea as the feathers on an arrow. They work by providing the necessary aerodynamic force to point the nose back towards the direction of flight after a perturbation. Have you ever thought about what you would do if you were in an airplane with a disabled pilot? Hopefully you wouldn't panic, because that's the worst possible thing you can do. If you're lucky to be on a Cirrus airplane, you have a parachute for the entire aircraft. All you have to do is pull the ripcord for the parachute. Pulling this will deploy the parachute for the entire airplane and take you down for safety. But if you're not in a Cirrus, what can you do? Well, you can fly the airplane. Let's talk through how that is, and it's not that difficult. The main controls are the throttle and the control stick. The throttle you can push forward to throttle the engine up to higher RPM to accelerate or climb, or you can pull back to descend or slow down. The control stick allows you to control the attitude of the aircraft: pitch, roll, and yaw. Pitch is controlled by pushing the stick in and out. So pushing the stick forward pitches the elevator such that the nose will point down. Or if you pull back on the control stick, the elevator will deflect upward, creating a downforce on the tail, which pitches the nose upward. Similarly, the roll control is by turning the stick to the right or to the left. Now, if I turn the stick to the left aileron will deflect upwards, the right aileron will deflect downwards. and that creates a rolling moment to turn the aircraft to the left. And then finally, to control the yaw of the airplane, I have rudder pedals at my feet. So I can step on the left rudder pedal to deflect the rudder to the left, and it'll turn the nose to the left. Or to the right, I can turn by pushing the right rudder pedal. Those are also useful for steering the airplane on the ground because they're also linked to the landing gear on the nose wheel. Those are the controls on the airplane. The plane will basically fly by itself. If it's trimmed up in flight, you really don't have to do a whole lot. But if you need to take it in for a landing, this is the way you can do it.
Now, like the earliest pilots and aerospace engineers, let's pause to wonder about the flight of birds, as well as aircraft. Clearly, there are vast differences in scale between a bird, such as a kestrel at half a pound weight, and a commercial airliner, such as an Airbus A380 at 1.2 million pounds, and vastly different cruise speeds, 22 miles per hour for the kestrel compared to 561 miles per hour for the A380. Are both really governed by the same physics? A useful metric for comparing these disparate flying bodies is called wing loading, which is an expression for how much load the wing is carrying. It's simply the weight divided by the wing area, which has the same units as pressure. It's not unlike the difference in loading on a floor for high-heeled shoes instead of flats. The high-heeled shoes have a much smaller contact area with the floor, which concentrates the same amount of load over a smaller area. In the same way, an aircraft with a smaller wing will have higher wing loading. Now, wing loading is connected to speed. The faster an aircraft travels, the more the lifting power is shifted from the wing area to airspeed. Since lift remains equal to weight, faster aircraft can have smaller wing areas, which drives up the wing loading. And it turns out that there is a large variation in wing loading for different flying birds and aircraft. For example, the kestrel, flying at 22 miles per hour, has a weight of only half a pound and a wing area of 0.76 square feet, giving a wing loading of about 0.6 pounds per square foot. The much larger wandering albatross, which cruises at up to 43 miles an hour with a weight of about 20 pounds and a wing area of 6.7 square feet, gives a wing loading of about 3 pounds per square foot. Then, let's take things up another notch. A popular light aircraft is the Beech Bonanza, which weighs 3,600 pounds and cruises at about 200 miles per hour. With a wing area of 181 square feet, the Bonanza has a wing loading of around 20 pounds per square foot. And finally, the mighty Airbus A380-800 has a wing area of 9,100 square feet, a maximum takeoff weight of 1.268 million pounds, and a cruise speed of 561 miles per hour. These specs give a wing loading of 139 pounds per square foot. So we're curious to see the implications of wing loading on flight. Let's take our lift equation and manipulate it slightly to reveal a stunning relationship that governs all flight. First, there's a fundamental to all of flight that is really important to establish at the outset. In equilibrium flight, whether it's a small bird or the largest commercial airliner, the forces must balance out in equilibrium. So for an aircraft in steady level flight, the lift must exactly equal the weight, and the thrust must be exactly equal to the drag. If these forces aren't in equilibrium, then the aircraft will be climbing or descending, accelerating or decelerating. So the forces must be in equilibrium for steady flight. Pilots and designers refer to this balanced condition as trim, or being in trim. Since the lift must be equal to weight, we can simply substitute that fact into the lift equation and rewrite the equation as a function of wing loading. If we make some simplifying assumptions and pick a value of air density of 1.25 kilograms per cubic meter, close to sea level density, and a typical value of lift coefficient of 0.6, we see that wing loading is equal to a constant times the square of airspeed. Now let's create a plot of the data for each flyer's weight as a function of airspeed and wing loading over a very wide range. This is termed the Great Flight Diagram, first put forward by Henk Tennekes in his book, The Simple Science of Flight. Let's plot data for our Kestrel, the Albatross, the Bonanza, and the A380, each with increasing weight, airspeed, and wing loading. And we can add data from numerous other flyers to the diagram.
we see that nearly all of the data collapses along one trend line across a range of 12 orders of magnitude in weight, 4 orders of magnitude of wing loading, and 2 orders of magnitude in airspeed. It's an absolutely stunning portrayal of the commonality of the physics of flight across a vast range of flyers. That now leaves us with a simple relationship between wing loading and airspeed, which works over a very wide range. At flight speeds above that of the A380, now there's some interesting additional physics that come into play as we start to approach the speed of sound. Air is compressible. Air slamming into a fast-moving aircraft bunches up near the leading edges because it can't move out of the way of the oncoming aircraft fast enough. The Mach number, defined as the ratio of the flight speed to the speed of sound, is a useful parameter to determine when the flow becomes compressible. The Mach number of the Kestrel is about 0.03, an extremely low Mach number where there are no compressibility effects. But the A380 cruises at a Mach of 0.85, where Mach effects become significant and begin to alter the aerodynamics. And if Mach number goes above 1, then flight is supersonic. And unique features such as shockwaves begin to form. Now, wing loading is one of the most important parameters governing the design and performance of aircraft. High-speed flight demands higher wing loading in order to keep the wings small and to reduce the drag that would impede that high-speed flight. But higher wing loading drives up the required runway length because an aircraft can't fly very slowly with a small wing. So the aircraft has to land at a higher speed and requires more runway to brake to a stop. And for optimal maneuverability, we have to have low wing loading. We need a large wing to produce lots of lift to pull the aircraft through a tight turn in a dogfight. For this reason, fighter pilots will dump fuel overboard before they engage in a dogfight. They want to be as light as possible for air combat with maximum maneuverability. Now, to summarize our discussion so far, we've seen 4 main forces that act on an airplane in flight. These are lift, weight, thrust, and drag. And for steady flight conditions, these must be in equilibrium. The lift must equal the weight, and the thrust must equal the drag. Now, these ideas actually touch on all the key subdisciplines in the science of flight. These are aerodynamics, the way air moves around wings, specifically making the lift from air as high as possible and drag from air as low as possible. Second, propulsion, efficiently and reliably producing thrust to keep the aircraft aloft and with a power loading that is reasonable. Third, structures, minimizing weight while efficiently holding the aircraft together with no risk of failure. And fourth, stability and control, dealing with rotations of the aircraft. This means keeping the aircraft pointed in the right direction, restoring equilibrium even when encountering a disturbance, and being able to make the aircraft go where we want it to go. Now, the earliest dreamers and pioneers of flight, like Leonardo da Vinci, were inspired by birds. However, the flapping wings of a bird are a combination of lift and propulsion. And except for a rare few ornithopters, humans still have not learned to fly that way. What humans discovered instead is that it's possible and easier for us to separate lift on the wings from propulsion by an engine. So the human approach to flight keeps those forces separated. Something else that we learned about lift is how to create flight vehicles lighter than air. In the next lecture, we'll turn to balloons, the very first form of human flight and the flight environment for all flight vehicles.